All right, welcome to the second derivative test video. I'm going to go through this. The second derivative test is kind of I don't want to say it's a useless test because it can be useful, but gets us to a place where it's more difficult to get there, if that makes sense. So I'm going to explain what it is, and then I'll get you on my side for that one. So second derivative test is going to determine if something's a local min or a local max. Now, we already know how to do that, and that's what I'm saying that the second derivative test is kind of like, It is useful in certain spots, though, and I'll kind of go over that when we get to the second question here on the second page. But second derivative test, what it does is you find the critical points, you don't make a sign chart, and you just plug those into the second derivative and then determine if it's concave up, concave down, and that will tell you if it's a min or a max. So for example here, first one says that if we have a critical point and we are concave down, so that means it's negative, then we have a local max, which makes sense because we're going to be concave down here. And if we have a critical point and we're concave down, well, that is a relative max. And then if we are concave up, that's what the second one says. So concave up, I don't know where I wrote up right there. This one I did CD. Oh, it looks better now. So concave up, that's going to be a minimum. And then for some reason, if the concavity is 0, then that tells us nothing. Can't use it. So then we have to go do something else. Which is why I'm not a big fan of the second derivative test, but if it asks us to use it, we actually do have to go through and use it. It's useful on some problems. It's not useful on others. So let's just get through it, and you'll see me griping about it probably by the end of the problem. Okay, so it says to use a second derivative test on this problem, if possible, to find where relative extrema occurs for this function. So we need to find critical points, and then we need to find the second derivative. So critical points means we need to find the first derivative, which is going to give me 15x to the fourth minus 15x squared. All right, we're going to need to set this equal to 0. Let's factor this more. So 15x squared is going to give me x squared minus 1. Factored even further, we're going to get x plus 1, x minus 1 on the right side. So we're going to have 3 zeros. So 3 critical points. All right, 0, -1, and 1. Now what I need to do with that is I need to plug it into the second derivative. So I need to make the second derivative. So let's go ahead and find that out right now. It's easiest to use this up here, not that down here, because that'd be a lot of product rule. So just go through up here and we'll figure this out. We'll get 60 x to the third minus 30x. And all we're trying to do is plug these numbers into here and figure out if it's positive or negative. Now, since we're just plugging it into here to find out if it's positive or negative, it's probably easier to factor this a little bit. You don't have to factor it, but I think it makes it easier to determine if something is positive or negative. So that's my second derivative, nice and factored. So I'm going to have my x value, and I'm going to plug it into my second derivative. I don't care if it's positive, negative, or 0. So let's go in numerical order here. So if I plug in a -1, I'm going to get negative times positive. So if you plug in a -1, the second derivative is concave down. Plug in a 0, you're going to get 0 times anything is 0. So you're going to get 0. Well, not really helpful. Plug in a 1, you're going to get positive times positive, which is positive. Now, I have all the information I need, and now I can go ahead and use the second derivative test to determine my extrema. So by the second derivative test, I have x equals -1. Now, that is concave down, and there's a critical point up here, so that's going to be a relative max because, and I'm just really going to go up here and restate this for the most part, because f prime of -1 equals 0, and f double prime is negative. And that's all you need. And then at x equals, I'll do 1 next, is a relative min, because f prime of 1 is equal to 0, and f double prime is positive. And then because we're told to use the second derivative test, well, at x equals 0, well, test fails. So I'm not going to worry about that for right now. If it did want more information, all you have to do is you'd make a sign chart right over here and you figure out what's going on. So that is the second derivative test. Now let's go ahead and see a problem where it actually is going to help us out a little bit here. So we have a function f that is continuous. I can't talk. Continuous on the second derivative for all x. That's nice. It says that it's twice differentiable, and that f of 3 is equal to -4, because it gives us all these values at 3. And let g be the function whose derivative is given by, I give this derivative here. Does g have a local maximum or a local minimum at 3? Justify our answer. So what we need to do is we need to figure out g prime. So actually, let's go with this. I don't have enough information to make a sign chart on this, because since I have the derivative, I can just find out, oh, when is it positive, when it's negative, but I don't have enough information on f. I just know at these certain points. So I can't use the first derivative test. So now I am handcuffed. I have to actually go ahead and use the second derivative test. So because I'm forced to use it, I need a couple things here. I need to make sure that g prime of 3 equals 0. And then I need g double prime of 3 and figure out what that is. Okay. Now this gave us g prime. Okay. So since we have g prime, we should go ahead and just check this real quick. So if you plug in a 3, you're going to get 0. Well, 0 times anything is 0. So this does work out. We're good. So I just need to find the second derivative here. And that's all that I care about. All right. Okay, so let's go ahead and find g double prime. Oh, no. A lot of product rule. Let's go for it. So the derivative of the first is going to be 2x. Leave the second, so 2f of x plus 5f prime of x plus, keep the first, and then the derivative of the second is going to be 2f prime of x plus 5f double prime of x. All right. Okay. Just trying to see what I should be getting here. Everything is all good. I'm ready to plug in our 3. When I do that, I'm going to get 2 times 3, which is 6, times, well, f of 3 is -4, so I'm going to get 2 times -4 plus 5 times f prime of 3 is 1. I'm just using all of my givens for this, plus 9 minus 9, which is going to give me a 0, which means I really don't care about all these numbers. So 2 times f prime of 1 plus 5 f prime of 3 is -2. This is going to 0 out, so I don't care about that. So I'm going to get 6 times -8 plus 5 plus 0, just to show you that it's all going to 0 out. And then we're going to get -18. So g double prime of 3 is -18. Okay. And that's it. So what do we have here? Is this a local maximum or minimum? So it's concave down. Again, if you want to draw it, down is a frown. That's going to be a local max. So it's going to be a local max at x equals 3. And then here you go. Because f prime of 3 is equal to 0 and f double prime of 3, and that is negative. And that's good enough. Now, the question I wish was worded a little bit better here. If it asked you to find all local maximum or minimums, then actually we would have to set this equal to 0 and find more points and then test them out. But we didn't have to. So it just asked about 3, and now we got it. And that is how you use second derivative test. Much more useful than the first problem, but it's how you use the second derivative test.